Welcome to module 4 of chapter 8. In this module we are going to study eigenvalues of well-known families of graphs. First we are going to give eigenvalues of a null graph, then we will find eigenvalues as well as eigenvectors of complete graphs. We will also find eigenvalues of Petersen graph, complete bipartite graph, etc. And we are going to characterize bipartite graphs by using eigenvalues of a graph. Finally, we are going to find eigenvalues and eigenvectors of circulant graphs. Module 4 of chapter 8 is about eigenvalues of some known graphs and diagraphs. The objectives of this module are eigenvalues of null graph, complete bipartite graph and Petersen graph. Characterization of bipartite graphs using eigenvalues. Eigenvalues of circulant graphs as well as diagraphs. First we are going to study eigenvalues of null graphs. The statement is, show that all eigenvalues of a graph x are 0 if and only if x is the null graph. If x is a null graph, then its adjacency matrix is the 0 matrix. As we know that null graph means that there are no edges at all. So, by definition of adjacency matrix, ijth entry is 1 if there is an edge from I to j, but in the null graph there are no edges, so every entry is a 0. So, the adjacency matrix of null graph is a 0 matrix. So, we already know that the eigenvalues of 0 matrix are zeros only. So, all eigenvalues are 0. So, we proved that if x is a null graph, then all its eigenvalues are 0. Now, conversely, using previous result we have that trace of a square, that is lambda 1 square plus lambda 2 square and so on lambda n square, where lambda 1, lambda 2 and lambda n are eigenvalues of A, which is equal to 0. So, that means conversely we are assuming that A is a 0 matrix or A is a null graph. Then we have that 0 is equal to 2 times number of edges, as we know that trace of A square is equal to twice the number of edges. So, consequently what happened? There are no edges, number of edges is 0, that means x has no edge. So, if there is no edge, then it is graph is going to be a null graph. Now, we are going to find out eigenvalues as well as eigenvectors of the complete graph Kn. First note that the adjacency matrix of Kn is equals to A, that is equal to all ones except and the diagonal elements. Diagonal elements are 0 and the remaining entire thing is 1. So, it can be written as simply j minus I. As we know that j is a matrix of with all ones. So, if you delete identity matrix from j, then we will get the adjacency matrix of Kn. So, this is a simple way to express the adjacency matrix of Kn. Thus, the eigenpairs, that is E comma n minus 1. As we observed, Kn is a regular graph with n minus 1 regularity. That means the degree of each vertex is n minus 1. So, Kn is n minus 1 regular. So, consequently, the vector E with all ones is an eigenvector of A. So, E comma n minus 1 is one eigenpair. Further, we noticed that Kn is a connected graph and also regular. So, n minus 1 the regular k is a simple eigenvalue. So, n minus 1 is a simple eigenvalue here. So, n minus 1 is an eigenvalue with multiplicity 1 and other eigenvectors are E1 minus Ei. So, where I ranges from 2 to n, where Ei is the standard basis vectors, that means Ei contains ith entry is 1, remaining all are 0. For example, E1 is 1, 0, 0 and so on 0. So, thus we have spectrum of Kn is n minus 1 1 times and minus 1 n minus 1 times. So, complete graph has exactly 2 eigenvalues n minus 1 and minus 1. Now, we are going to find out the eigenvalues of Kmn. The adjacency matrix of Kmn has rank 2. So, here it is easy to show. So, since the Kmn is a bipartite graph, though vertices are divided into two groups V1 union V2 equal to V, there is no edge from vertices of V1 elements in V1, there is no edge from elements of V2. So, the matrix looks very nice, that is the V1 to V1 part is completely 0, V1 to V2 part is completely J, similarly V2 to V1 part is completely J and V2 part is a 0 matrix. That is why the rank of Kmn is 2. So, lambda equal to 0 is an eigenvalue with the multiplicity m plus n minus 2. Let lambda 1 lambda 2 be remaining two non-zero eigenvalues as trace of A is equal to 0, trace of every adjacency matrix is 0. So, lambda 1 plus lambda 2 plus all our other eigenvalues are 0. So, lambda 1 plus lambda 2 equal to 0 or lambda 1 is equal to minus lambda 2. Further, we know that trace of A square is twice the number of edges. The number of edges in Kmn are m into n. So, we have lambda 1 square plus lambda 2 square, which is equal to 2 times lambda 1 square is equal to 2 times m into n. So, we have lambda 1 is equal to root of mn. So, consequently, lambda 2 is minus root of mn. Thus, the spectrum of Kmn is minus root mn one time, 0 m plus n minus 2 times and root mn one time. So, complete bipartite graphs have 3 distinct eigenvalues. One is root minus mn, other is 0 and root mn. Now, we will find eigenvalues of Petersen graph. Since Petersen graph is strongly regular graph with parameters 10, 3, 0, 1. So, A square plus A minus 2i into I is equal to j. So, eigenvalues of A are 3 because Petersen graph is a 3 regular graph, 3, so 3 is one of the eigenvalue, and since Petersen graph is connected, so 3 is a simple eigenvalue of A, and the remaining eigenvalues are going to be roots of the equation x square plus x minus 2 equal to 0. Thus, the distinct eigenvalues are 3, 1, minus 2. Let the multiplicity of 1 be s and that of minus 2 is be t, then we know that from trace of A is equal to 0 and trace of A square is twice the number of edges, we have that sum of the eigenvalues 3 plus s minus 2t. It is because 1 is an eigenvalue with multiplicity s. So, we have 3 plus s minus 2t equal to 0 and squares of the eigenvalues, sum of the squares of the eigenvalues, that is 9 plus s plus 4t is equal to 2 times number of edges. Number of edges in Petersen graph is 15. So, we have two equations, one is 3 plus s minus 2t equal to 0, 9 plus s plus 4t is equal to 30. By solving these two equations for s and t, we will get s equal to 5 and t equal to 4. Thus, the eigenvalues of Petersen graph including multiplicities are 3, 1, 1, 1, 1 5 times, minus 2 4 times. Now, we will prove an important result. This theorem states that there is no decomposition of edge set K10 into 3 disjoint copies of the Petersen graph. So, first observe that the degree of K10 is 9 and degree of Petersen graph is 3. So, generally one inspired with this, people look for, there is a possibility of writing K10 as disjoint copies of Peterson graph, but this result says that it is not possible. It is not possible to write K10 as sum of 3 disjoint copies of Peterson graph. We will prove the result by contradiction. That means, we will suppose that the edge set of K10 can be decomposed into 3 disjoint copies of Peterson graph. Let P be the adjacency matrix of Peterson graph. Hence, according to our assumption, adjacency matrix of K10 complete graph, which is equal to J minus I, which is equal to P plus Q plus R, where P is the adjacency matrix of the Peterson graph and Q and R also adjacency matrix, but by relabeling them, that is Q equal to S1 into P S1 transpose, which is also equal to S1 into P S1 inverse, and R is equal to S2 P S2 inverse for distinct permutation matrices S1 and S2. As Q and R are similar to P, so Q, R have same eigenvalues as P. So, consequently, from the previous exercise, the eigenvalues of P, Q and R are 3, 1, minus 2, and further 3 is an eigenvalue with multiplicity 1 is an eigenvalue with multiplicity 5, minus 2 is the eigenvalue with multiplicity 4 for all these matrices P, Q, R. Moreover, E is an eigenvector corresponding to eigenvalue 3 for both P and Q. So, now consider the eigenspaces. WP is equal to set of all vectors, real vectors, Px equal to x. That means, we are finding eigenvector corresponding to eigenvalue 1. Similarly, WQ is equal to all vectors Qy is equal to y. That means, all eigenvectors corresponding to eigenvalue 1. We know that dimension of WP is equal to dimension of WQ equal to 5. It is because this P and Q are symmetric matrices. So, their algebraic multiplicity is equal to geometric multiplicity for each and every eigenvalue. That is why dimension of WP equal to dimension of WQ is equal to 5, as multiplicity of 1 as an eigenvalue of Peterson graph is 5. Also, for each x belongs to WP union WQ, we have E transpose into x equal to 0. As P and Q are symmetric matrices, we know that one can find eigenvectors such a way that they are mutually orthogonal. So, further we know that E is one of the eigenvector of P and Q. So, this is possible. So, x is perpendicular to E or x belongs to E perp, but dimension of E perp is equal to 9. So, hence dimension of WP intersection WQ is greater than or equal to 1. We now claim that WP intersection WQ is equal to empty. Once if you show, then we are going to get a contradiction. Hence, we arrive at a contradiction. So, if Z belongs to WP intersection WQ, then we have that E transpose into Z equal to 0, as E is an eigenvector. Thus, RZ is equal to J minus I minus P into minus Q into Z, which is equal to 0 minus 1 minus 1 minus 1 into Z, that is equal to minus 3Z. So, a contradiction as minus 3 is an eigenvalue of R. Thus, required result follows. Here understand that WP intersection WQ is empty means there is at least 0 vector is always be there. So, WP intersection WQ contains only 0 vector. Now, we study eigenvalues of bipartite graphs. Let x be a bipartite graph and let lambda be an eigenvalue of x with multiplicity m, then minus lambda is also an eigenvalue of x with the multiplicity m. Let us relabel the vertices of x so that the adjacency matrix of A has the form A is equal to 0 matrix B, B transpose 0, where B is a matrix of size n1 cross n2. Now, let ui is xi yi for some 1 less than or equal to I less than or equal to m be the eigenvectors of A corresponding to eigenvalue lambda. Xi is of the size n1 cross 1 and yi is a size of size n2 cross 1, where n1 n2 are the cardinalities of the bipartition. As you know that X is a bipartite graph, so vertex at V is equal to V1 union V2. So, the cardinality of V1 we are assuming as n1, the cardinality of V2 we are assuming as n2. Then by definition, lambda times xi yi is equal to lambda ui, which is equal to aui. So, which is equal to 0 b b transpose 0 into xi yi. So, which is equal to byi into b transpose xi. Thus, lambda into xi is equal to byi, lambda into yi is equal to b transpose xi. Now, we will define Vi is equal to xi minus yi, then it can be verified that Vi's for 1 less than or equal to I less than or equal to m are eigenvectors of x corresponding to eigenvalue minus lambda. As the vectors Vi's are linearly independent, as U's were linearly independent, hence the required result follows. So, hence what we proved here is that if lambda is an eigenvalue with multiplicity m, then minus lambda is also an eigenvalue with multiplicity m by constructing the eigenvectors suitably. Now, we will prove another result. Let X be a connected graph with n vertices, m edges and no triangles, then m is less than or equal to n square by 4. So, number of edges is less than or equal to n square by 4 whenever the graph does not have triangles. So, it is very less, means once if the graph does not contain triangles, number of edges reduce drastically. Let A be the adjacency matrix of the graph X and lambda 1 greater than or equal to lambda 2 and so on greater than or equal to lambda n be its eigenvalues. Let us suppose that m is greater than n square minus n square by 4. We are proving by contradiction. Actually, we have to show that m is less than or equal to n square by 4, but we are assuming m is greater than n square by 4, that is root m by n by 2 is greater than 1. This can be m is greater than n square by 4 can be written as root m by n by 2 is greater than 1. From the previous result, we have that lambda 1 is greater than or equal to 2m by n, the largest eigenvalue is greater than or equal to average degree 2m by n. So, that is equal to 2m by n can be written as root m into root m by n by 2. So, this is greater than root m, as root m by n by 2 is greater than 1. So, root m into root m by n by 2 is greater than root m. Thus, 2 times lambda 1 square is greater than 2m, but 2m is equal to trace of a square, as trace of a square equal to twice the number of edges. So, which is equal to lambda 1 square plus lambda 2 square and so on lambda n square. So, which is can be written as lambda 1 square plus summation 2 to n lambda I square, or lambda 1 square is greater than summation 2 to n lambda I square. Recall that lambda 1 is greater than or equal to mod lambda I for 2 less than or equal to I less than or equal to n. So, summation 2 to n lambda I cube is less than or equal to summation 2 to n modulus of lambda I cube less than or equal to lambda 1 times summation 2 to n lambda I square, which is less than or equal to lambda 1 cube. Consequently, 1 by 6 times summation I is equal to 1 to n lambda I cube, which is equal to lambda 1 power 6 by summation 2 to n lambda I cube by 6. This is greater than 0, but 1 by 6 of trace of A cube is the number of triangles. That means, we are showing that number of triangles is greater than 0. That means, the graph has at least one triangle, which is a contradiction. It is because we are assuming that graph has no triangles. So, we got the required result. Now, we are going to, as a corollary to this, one can see easily that let X be a bipartite graph with n vertices, then it has at most n square by 4 edges. Since every bipartite graph, every cycle length in a bipartite graph, the cycle length is always even. So, it automatically does not contain the triangles. In fact, we can prove more. This result we already established without using the adjacency matrices or eigenvalues, but so now this can be derived very easily from the previous result. Let X be a bipartite graph with bipartition C comma D, where cardinality of C is equal to cardinality of D is equal to n. Then its adjacency matrix A has size 2n cross 2n. Let sigma be a permutation of 1, 2, 3 and so on 2n, and let we will define value of sigma, the permutation sigma, as I is equal to 1 to 2n, I lambda ith entry of A, we are multiplying all this. Then it is known that determinant of A is equal to summation sigma belongs to S to n sin of sigma into value of sigma. So, where for any permutation sigma, sin sigma is the signature of sigma, that is either plus 1 or minus 1. Then we have the following results. The permutation sigma corresponds to a perfect matching if and only if value of sigma equal to 1. The graph X has only one perfect matching if and only if determinant of A equal to plus or minus 1. A tree is said to have perfect matching if it has a spanning forest whose components are paths on two vertices only. We showed that 0 is the only eigenvalue of the graph if and only if the graph is a null graph. The eigenvalues of complete graph are minus 1 and n minus 1. N minus 1 is an eigenvalue with multiplicity 1. We also showed that the eigenvalues of complete bipartite graph Kmn are root of minus root of Mn, 0 and root of Mn. 0 is an eigenvalue of complete bipartite graph with multiplicity m plus n minus 2. We proved an important result. A graph is bipartite if and only if its eigenvalues are symmetric about origin. In fact, one can prove more. If lambda is the largest eigenvalue of the graph X, then X is bipartite if and only if minus lambda is an eigenvalue of the graph X. Now, we will study circulant matrices. For that, we need adjacency matrix of a directed cycle. Let Wn be the adjacency matrix of a directed cycle with n vertices. Then Wn is equals to 0, 1, 0, 0 and so on, 0, 0, 1 and so on 0, and last row is becomes 1, 0, 0 and so on 0. Clearly, it is a permutation matrix. You can see that there is a directed edge from 1 to 2, 2 to 3 and so on n to 1. So, that is what this matrix is about. So, now onwards we denote Wn means the adjacency matrix of a directed cycle with n vertices. So, it is defined exactly like this. The minimal polynomial of Wn is x power n minus 1, hence the eigenvalues of Wn are nth roots of unity. That can be verified easily. So, once if you evaluate Wn, Wn square and so on, Wn power n becomes identity. So, since it is a permutation matrix, so some power has to be identity, but exactly in this case Wn power n is equal to identity, and further the all the roots of x power n minus 1, the nth roots of unity are distinct. So, x power n minus 1 is not only the minimal polynomial of Wn, it is also the characteristic polynomial of Wn. So, the directed cycle, all its eigenvalues are nth roots of unity. Now, we define a circulant matrix. A matrix A belongs to Mn of f, that means a set of all n by n matrices with entries from f. Actually, one we can consider f is the complex number, set of complex numbers, is said to be circulant matrix if Aij is equal to A1 j minus I plus 1 mod n, that is for each I greater than or equal to 2, the elements in the ith row of A are obtained by cyclically shifting the elements of I minus 1th row of A, one position to the right. So, it is sufficient to specify its first row. So, circulant matrices are nice matrices, no need to specify all the n square entries, just if you specify first row, then we will get all other rows. It is easy to see that Wn is a circulant matrix of order n with its first row as 0, 1, 0, 0 and so on 0. Then the following result is stated without proof. The proof can be done easily. Every circulant matrix is a polynomial in Wn. That is, the lemma says that let A belongs to Mn of f, then A is circulant if and only if it is a polynomial in Wn. That is, the set of all circulant matrices in Mn of n forms a commutative algebra. Note that as a vector space, its basis is identity matrix Wn, Wn square and so on, Wn power n minus 1. In fact, it is easy to see that identity Wn power 1 and Wn square and so on, Wn power n minus 1, this forms a cyclic group. It is because Wn power n is again identity. So, they are not only just basis, they have a nice texture, and further one can easily check that if you add all of these matrices identity Wn, Wn square and so on, Wn power n minus 1, we will get the matrix J, that is matrix with every entry is 1. So, let A be a n by n matrix with integer entries, be a circulant matrix, then by previous lemma there exists a unique polynomial lambda a of x, gamma a of x belongs to z of x of degree less than or equal to n minus 1. In fact, one can take Mn of complex numbers, that means we can assume the circulant matrix with complex entries also, still the result is true, but usually we are confined to 0 1 matrices, that is why we are taken here Z, but one can take entries from complex numbers also. Then this polynomial is called a representative polynomial of A when if A is equal to gamma A of Wn. That means the circulant matrix is a polynomial in Wn, that polynomial is called representative polynomial of A. Further, one can see that if A belongs to Mn of Z is circulant matrix, then A0, A1 and so on An minus 1 is the first row of A if and only if gamma of A is equal to A0 plus A1x and so on plus An minus 1 x power n minus 1. That is, representative polynomial also can be evaluated easily by using the first row of A. Similarly, if you know the representative polynomial, then we know the first row of A, so consequently we know entire matrix A. Consequently, there is a one-to-one correspondence between the set of all circulant matrices over C and set of all polynomials over C of degree less than or equal to n minus 1. In particular, there is a one-to-one correspondence between set of all 0 1 circulant matrices and set of 0 1 polynomials of degree less than or equal to n minus 1. Now, we will find eigenvalues of circulant matrices, circulant graphs. Actually, a circulant graph means a graph is said to be circulant graph if its adjacency matrix is a circulant matrix. So, there is not much difference. Circulant graphs are simply the graphs whose adjacency matrix is a circulant matrix. let zeta n is a primitive nth root of unity, that is zeta n power n equal to 1, but zeta n power k not equal to 1 for 1 less than or equal to k less than or equal to n minus 1, one can choose zeta n as e power 2 pi I by n, then it will satisfy these conditions. Then it is easy to verify that W n into 1 zeta n so on zeta n power n minus 1 is equal to zeta n times 1 zeta n and so on zeta n n minus 1. So, what we are showing here is that zeta n is an eigenvalue and 1 zeta n and so on zeta n power n minus 1 is corresponding eigenvector. Now, lemma, let A be a circular matrix with representer polynomial gamma A of x. A is diagonalizable with gamma A of zeta n power k for 0 less than or equal to I less than or equal to n minus 1 as its eigenvalues. So, the previous result is easy to show. We already proved that if the lambda is an eigenvalue of A and q of x is any polynomial, then q of lambda is an eigenvalue of q of A. So, with that we will get that result. Let A be the adjacency matrix of a cyclic graph Cn, then lambda A of x, the representer polynomial of A is equal to x power n minus 1. That is, the adjacency matrix of cyclic graph Cn is Wn plus Wn power n minus 1. It is better to check. So, its eigenvalues are given by lambda r is equal to 2 times cos 2 pi r by n for r is equal to 1, 2, 3 and so on n minus 1. It is easy to see that lambda r is equal to lambda n minus r, that means there is a repetition of the eigenvalues. As the diameter of Cn is floor of n by 2 and Cn has floor of n by 2 plus 1 distinct eigenvalues and the dimension of adjacency algebra of Cn is equal to floor of n by 2 plus 1, the following result shows that the cyclic graph is a distance polynomial graph, that is its distance matrices belong to adjacency algebra. In fact, they form the basis for adjacency algebra. So, theorem is the cyclic graph is a distance polynomial graph. Proof, it is easy to see that for a cyclic graph Cn, the distance matrices are Ai is equal to Wn power I plus Wn power n minus I for 1 less than or equal to I less than or equal to floor of n by 2. For gamma, if you take tau is equal to floor of n by 2, then A tau is defined as Wn power tau if n is even, and A tau is equal to Wn power tau plus Wn power n minus tau if n is odd. And the identity, if you use the following identity, that is x power k plus x power minus k is equal to x plus x inverse into x power k minus 1 plus x power 1 minus k minus x power k minus 2 plus x power 2 minus k, enables us to establish readily by mathematical induction that x power k plus x power minus k is a monic polynomial in x plus x inverse of degree k with integer coefficients. So, this is going to be useful for us. Consequently, AIs, that is 1 less than or equal to I less than or equal to tau, are polynomials of degree less than or equal to I in A1 over Q. Hence, A0, A1 and so on A tau is a basis for E of Cn. The following result shows that every symmetric circular matrix is a polynomial in the cyclic graph. Hence, the eigenvalues of every symmetric matrix can be computed using eigenvalues of Cn. Again, circulant graph means whose adjacency matrix is a circulant graph, circulant matrix, and further it is a symmetric circulant matrix. So, theorem is that if B belongs to Mn of Q, in fact one can take even complex numbers also, B is symmetric circulant if and only if B belongs to adjacency algebra of Cn. Proof, by the definition of adjacency algebra of the graph, every element in adjacency algebra of Cn is a symmetric circulant matrix. We now show that B is a symmetric circulant matrix, then B belongs to adjacency algebra of Cn. Let B be a symmetric circulant matrix with representer polynomial gamma B of x equal to summation I is equal to 0 to n minus 1 B I x power I. Then B is equal to I is equal to 0 to n minus 1 B I into W n power I, and B transpose is equal to summation I is equal to 0 to n minus 1 B I W n power n minus I as well. Consequently, B I is equal to B n minus I for 1 less than or equal to I less than or equal to n minus 1, as B equal to B transpose. From that we will get this. So, hence B is equal to summation I is equal to 0 to n by 2 B I A I, where A is the distance matrix of the cyclic graph. Hence, the result follows. We showed that every circulant matrix is a polynomial in Wn, where Wn is adjacency matrix of directed cycle. We also showed that every symmetric circulant matrix is a polynomial in adjacency matrix of cycle graph. If A is a circulant matrix, then there exists a polynomial q of x such that q of W1 is equal to A. That is why the eigenvalues of A are nothing but q of lambda, where lambda is a nth root of unity. We also showed that all circulant matrices have same set of eigenvectors, as they are all polynomials in Wn. The eigenvectors of Wn are automatically eigenvectors of every circulant matrix. With this, we end this module.